Okay, so welcome to the 44th video in the Discrete structure series, and this is going to be the last video in the topic of permutations and combinations. And the topic for today is called generating permutations and combinations. So far, we have approached permutations and combinations as a problem in counting. For example, we are interested in how many ways we could choose n things taken r at a time with regards to the order. And similarly, we looked at combinations as a concept of counting from a set of n things taken r at a time without respect to the order. And then we looked at more generalizations from these concepts, like indistinguishable objects and repeated objects. But the focus of our study was still scoped to counting. But here, instead of counting, we are looking at the word generating. For example, we know that the combination of 5 things taken 3 at a time is equal to 10. But if I am actually given a set of 5 objects, how do we actually generate or list the 10 different combinations of 3 objects? So looking through it systematically, the first topic that we're going to see is generating permutations. And here we'll study an algorithm for listing the permutations of n objects taken all at a time. And that would be listing the n factorial different permutations. The next thing that we'll look at is called generating combinations. And in here, we'll describe an algorithm of generating the combinations of n things taken r at a time. So this will be one algorithm that we'll look at. But we'll also quickly look at an algorithm for all combinations, or I should rather say combination of all lengths. And just to give you a little bit of perspective, let's say if I have a set of A, B and C, I know that there are 3 combinations of length 1. They're just going to be A, B and C individually. Of length 2, I'm going to have 3 combinations as well. I'm going to get AB, BC and AC. Remember, the order doesn't matter. I'm looking at combinations. And if I look at the combination of length 3, there's only one combination that includes all of A, B and C. So later when we look at this algorithm for generating combinations, the CNR algorithm will allow us to choose a value of R. So we are going to be able to say we want R is equal to 2, and that would only give us these 3 combinations. And there's this other algorithm that generates the combination of all lengths. So in this algorithm, I'm not allowed to specify a specific value of R, and it will generate all of these combinations. So this will be the scope of today's video. And if you are wondering about one more topic, let me list that here, Pn, R. This is actually not given in our syllabus, and we'll keep this as a small surprise on the end. Alright, with that scope, let's get started with generating permutations. Alright, so our goal in this topic is going to be able to give an algorithm to generate the n factorial different permutations of n objects taken all at a time. So first we'll look at the concept here. So let's say I want to list all the permutations of these letters. Let's say A, B and C. Or we could be considering permutations of 4 people, or the permutations of all the cities that someone could visit. Regardless of what items belong to my set, the first observation that I want to make is that the problem of generating the permutations of n objects is the same as generating the permutations of the numbers 1 to n. So why is this true and why is this useful? First, let's see why it is true. So let's say I want to find all the different permutations of A, B and C. What I can do is simply apply a tag on each of them. So I can label a 1 on this A. I can apply a tag, let's say a label of 2 on this B and a 3 on the C. And now I want to forget about A, B and C and work with 1, 2 and 3. I don't know how yet, but I want to be able to generate all the different permutations of 1, 2 and 3. Let me even write the permutations here quickly. So these are the 6 permutations of 1, 2, 3, and let us for now assume that I'm able to generate these. Now what I can do at the end is simply replace the labels with their original values. So the permutations of the labels 1, 2, 3 represent the permutation A, B, C. The permutation 2, 3, 1 for example represents B, C, A. And we could follow the same argument for any set with any number of elements. For this set with 4 elements, I would simply choose the numbers 1 through 4, list all the different permutations and then retrace the values back. And in general, for any set of n elements, I could assign each element uniquely to a number from 1 to n. And therefore, the problem of generating the permutation of n objects is the same as generating the permutations of 1 to n. So the fact that this works is established. I hope you can agree with that. But then why is it useful? You see, the usefulness comes from the fact that the numbers have a certain order. To be more precise, whenever I'm listing all of these permutations, I want to somehow be able to keep track of which permutations I have already listed, so that I can form a system and not repeat. And I can exploit the fact that certain numbers appear before certain others. Here I've simply listed all of these in random order. But our goal is to be able to form a system whereby looking at one single permutation, we can tell exactly how many were listed before it and what the next permutation should be. And the way we achieve this is something called a lexicographical ordering. And this simply means dictionary ordering, the way words are ordered in the dictionary. And in fact, this is the basis of the algorithm that we are going to design here. But before we do the algorithm, let us look at an example of how this works. So let us take the same example with 1, 2, and 3, but now we'll follow the algorithm. And before even looking at it technically, let us see what the next word in the dictionary would be. See, the only possible letters are 1, 2, 3. And every permutation of 1, 2, 3 is a possible word. And if those words were listed in the dictionary, what would the next word be? The first thing that you need to agree that the very first word is going to be 1, 2, 3 itself. Because there is no number made with 1, 2, and 3 that comes before this. And if we want to follow the dictionary ordering, the next number would be 1, 3, 2. Now there are no more words that start with a 1 anymore because we have looked at both permutations of 2 and 3. So in the dictionary, the next lexicographical ordering should start with 2. And we know the other characters 1 and 3 will just be in the ascending order. So 2, 1, 3 will be the next word in lexicographical ordering. So after this, the next word, I think you would have guessed, would be 2, 3, 1. And now no more starting with 2. And therefore the last two words will be 3, 1, 2 and then 3, 2, 1. So this type of ordering is called lexicographical ordering. And if you look into these numbers as a whole, you'll see that each number increases. So 123 becomes 132, becomes 213, 231, 312 and 321. So you see it is strictly in ascending order. But we need to look at this a little bit more closely and see what's exactly happening and how we are making a transition from one step to another. So let me give you a slightly longer example and we'll look for a pattern. So let's say I started with 6 numbers and not 3. 1, 2, 3, 4, 5 and 6. Now following lexicographically, I know the second number is gonna be 4, 6, 5. Now this obviously has a lot of permutations, 6 factorial actually, but what we wanna be able to see is the pattern. So let's say we keep going on, applying the same rule, and let's say we reach this number, 2, 3, 4, 1, 6, 5. So this number is completely random, there's nothing special on it, but it will make observing the pattern a bit easier. So in order to find what comes after this, you wanna start looking from the last number and find one such number that is smaller than the previous number. If I look at 5, there's nothing before 5. I move on. When I move to 6, I see that 6 is a number bigger than 5. Therefore, I move on. I reach a 1. And 1 is not bigger than 6. So 1 is the number that I have found. So let me repeat the logic again. Look from the end towards the left and find the first number that is not in ascending order. So 5 and 6 are in ascending order and 1 is not. Everything to the left of this 1 will remain the same. So in the next permutation, 2, 3 and 4 will remain exactly the same. Now in place of this 1, something else will arrive. And we know that has to be one of these two things. And for our case, listen carefully. We want to find the smallest number that is bigger than 1. So this is my target number 1. So the number that I'm looking for here should be bigger than 1. But I want to find the smallest number that has that property. So among 6 and 5, 6 is also bigger than 1. 5 is also bigger than 1. But I want to choose 5 and not 6 because 5 is the smaller. And therefore this 5 will be replacing the 1. Once I do this, there are 2 more positions remaining. And this part is actually quite simple. The remaining things will just go in ascending order. So the remaining things are 1 and 6. They will just go in ascending order. And therefore the next permutation from 2, 3, 4, 1, 6, 5 is just 2, 3, 4, 5, 1, 6. So this is the generalization that you want to be able to observe. And we did the same thing in each of these steps. So if we started with 2, 1, 3. So if I look at 3, it's fine. But 1 is not ascending, right? So 1 is the number that is in descending order when I look from the end. So everything before the 1 will remain the same. That means the first 2 will be the same. And something needs to replace the 1. In this case, there is only 3 to replace the 1. So 3 and then 1 will go to the end. So 2, 3, 1 is the next permutation after 2, 1, 3. But I hope you see this doesn't clarify the entire point. And that's the reason I chose 6 digits. Okay, let's keep going. Let's say we eventually reach 362, 541. Again, a random number. Now like before, you start looking from the end and find the first number that is not in ascending order. So 1 followed by 4, that is fine. 4 followed by 5 is fine. But after 5, I have a 2. So 2 is the first number that is not in ascending order when looking from the right. So to generate the next permutation, the left part will be the same. 3, 6 will be the same. Now in place of these 2, 1 of 5, 4 or 1 should be placed. And we know that I'm looking for the smallest number that is greater than 2. Although 1 is the smallest number, I cannot take it because I want a number greater than 2, and I don't want to take 5 because 4 is still greater than 2 and less than 5. So the number of my choice is 4. The 4 will go here, and there are 3 positions remaining. And what are the 3 things remaining now? I hope you can see 2, 5 and 1 are remaining. They'll just go in ascending order. 1, 2, 5. So this is the next permutation. And let's make one last observation. We know that all of these numbers are strictly increasing. Each new number that we generate is bigger than the previous number. So eventually we'll hit this number 6, 5, 4, 3, 2, 1. And if I apply the same logic, try to find the first number that is not in ascending order, I cannot do that. Because 1, 2, 3, 4, 5, 6, the entire thing is in ascending order, and therefore there is no next permutation. So in case of 6 items, 1, 2, 3, 4, 5, 6 is going to be my first permutation, and 6, 5, 4, 3, 2, 1 is going to be my last permutation. And given each permutation, we know exactly how to generate the next permutation. Alright, now we're ready to do the algorithm. So let me make a little bit of space here. I'll just leave the example for context. And okay, let's do the algorithm here. So we'll write the procedure for next permutation. So I'll say next underscore permutation, and it takes the current permutation as an argument. So let's say the current permutation is represented by A1, A2, all the way to AN. And I want to make sure that this permutation is not equal to n minus 1, n minus 2, all the way up to 3, 2, and 1. Why? Because I know this is the last permutation. In this example, it is equivalent to saying 6, 5, 4, 3, 2, 1. Starting from the largest number and reaching all the way to 1. So if I input that, I'm not going to get the next permutation. And you should also acknowledge that this is not a procedure to generate all permutations. This is just a procedure to generate the next permutation. But if you want to be able to generate all permutations, this is still going to be the heart of your process. So you want to write an external procedure or a loop that starts with 1, 2, 3 and calls the next permutation function. And every time this returns a permutation, you want to store that permutation and call the next permutation again. So you'll keep doing that until it returns the last permutation. And you know what the last permutation should be? It should simply be the reverse of the first permutation. So just remember that in the back of your head, that this algorithm is just for the next permutation, but this should be enough for all purposes to generate all combinations if needed. Alright, so what do we want to do first? We want to find the first number. Looking from the end, we want to find the first number that is smaller than the previous number. For example, in this case, we said 5, 6 were ascending, and 1 was the first number that was smaller than 6. So on the algorithm side, we'll just be comparing pairs. So we'll be comparing 6 and 5 first. And if 6 is already less than 5, we stop. 6 is what we found. But here 6 is greater than 5, so we just shift to the left. We look at 1 and 6 next. And we find that 1 is less than 6, so we stop at 1. In this case, we do the same thing. We look at 1 and 4. 4 is not less than 1, then we shift. We look at 4 and 5. 5 is not less than 4, shift again. Look at 2 and 5. 2 is less than 5, so 2 is what I'm looking for. So my first job is to find the index, not the number, but the index or the position. And that position should be the first index from the end with this property. So let us try to do that. So for this number, I want to look at this number for an example, 362541. So let me put a marker on this 4, okay? So I have a total of 6 numbers here, 362, 54 and 1, which is equal to my n. So the value of my n is equal to 6. And I want to put a marker here, and I want to do that here by saying that j is equal to n minus 1, okay? So j is the position of my marker, which initially I want to put at the second last element, n minus 1. Now what is the logic? If this element is less than the previous element, I stop. Otherwise, I shift. So in this case, 4 is not less than 1, so I must shift and check. 5 is not less than 4, so I shift again. And 2 is less than 5, so I stop. So even though I'm comparing two numbers, I'm only using one marker. Because once I have the marker, I already know what the next number should be or what the next index should be. I hope that is clear. So currently my marker is at the second last index, j is equal to n minus 1. And I want to say while aj greater than aj plus 1, just decrease j. J is equal to j minus 1. So aj is the number where my marker is at, and aj plus 1 is the next number. So if the number where my marker is greater than the next number, I need to shift. That means I need to decrease j. Let me actually clean this and show you even better. 362541. So first I put my marker j on the second last element over here. And now I test this while condition. Is aj greater than aj plus 1? Is 4 greater than 1? Yes. In that case, I simply need to decrease j. Decreasing j means moving the marker to the left. The while loop condition is tested again. Is aj greater than aj plus 1? Is 5 greater than 4? Yes. The marker is shifted again. Remember, now marker is here. Marker is at the position j is equals to 3 in this case. And now we ask the same question. Is aj greater than aj plus 1? Is 2 greater than 5? No. That means the while loop will stop. We'll write what happens next here. But you should understand that when the while loop terminates, j is the largest index with aj less than aj plus 1. And the point of this entire statement is, it is the first index where the number breaks the ascending pattern. So 1, 4 and 5 are ascending and 2 is descending. And that is characterized by aj being less than aj plus 1. And we can also be confident that we have found the largest index because we started looking from the right. Since we started looking from the end, the first thing that we found was the largest index compared to the left. Alright, so now I have found this index. What do I do next? The next thing that I want to do is to find out what needs to replace the 2. Out of the remaining elements to the right, I need to find the smallest number that is greater than 2. We knew in this case that would be equal to 4. So how do we find that? So that part is also quite simple. I'll just put a marker at the end and keep decreasing it until I reach this position just to the right of my previous marker. And for each number that I find, I'm going to keep track of the smallest number that is greater than 2. So let me just say k is equals to n. So this means I have now placed my marker here over at 1. And now I want to say while aj greater than ak. So when we say aj greater than ak, you have to understand that aj is just a number that I found earlier. aj is always going to be 2. And I want to find the position k for this number 4, which is greater than 2 and the smallest number that has that property. So when I place my marker over here, I want to make sure that I place my marker on a number that is greater than 2 because that is one of my requirement. From the remaining numbers, I want a number that is greater than 2. But if that is not the case, if this 1 is not greater than 2, what will happen? The 2 will by itself be greater than 1. So if 2 is greater than 1, I am not happy. I need to keep moving left, keep finding another number. So while aj is greater than ak, I need to keep shifting. I want to reduce k by 1. So when that happens, I'll remove the marker from 1 and place it on this 4. That will be the value of my k. And then we check that again. Is aj greater than ak? Is 2 greater than 4? No. 2 is less than 4, which is what I need. The while loop will stop. And therefore the position where the k is pointing is going to be the least number that is greater than 2. Let me clean this up one more time and demonstrate. So I started with 362541. When the first while loop terminated, I found the first number that is not in ascending order. So I figured out that this would be my j, the position of j, and the value of my aj would be equal to 2. Now from the remaining 3 numbers, which I know are already ascending, looking from the right, I want to find the first number that is greater than 2. So 1 is not greater than 2, but 4 is greater than 2. So I do that by comparing these 2 with each of these numbers. If 2 is greater, I keep moving left. But if 2 is not greater than this number, I stop. So I do that by applying k is equals to n, which is the same as placing a marker on this 1. But for this position, aj greater than ak will be true. Therefore, k will be reduced and it will point here. And for this position, ak will be equal to 4 and therefore aj greater than ak will no longer be true. And so this while loop will also terminate. We can say when this while loop terminates, we are confident that ak is the smallest number greater than aj to the right of it. So I've located my 2, I've located my 4. The next thing that I want to do is interchange. Alright, so after interchanging aj and ak, let me mention here what it looks like. So it looks like 3, 6, 2 will be replaced by a 4, 5, 2, 1. And remember, this is the position j and this is the remainder of the right. But we have already replaced the 2 with a 4. But we still need to fix the rightmost part, 5, 2, 1. And all we want to do is to sort this in ascending order. Now, the process to sort this in ascending order will not require a full sorting because it is already in descending order. Because from the algorithm itself, we are making sure and finding the first number which is breaking the descending pattern or the ascending number pattern looking from the right. And therefore, when we find such a number and make a replacement, this number sequence will still be ascending, but it will be ascending looking from the right. So all we want to do is to reverse this sequence. Now let me tell you a few things about reversal. So let's say I want to reverse this sequence 5 to 1. I'm just taking a subset from here, 5 to 1, which I want to reverse, and doing that will put it in ascending order, the order that I want. So the algorithm that we use here will use two markers and we'll keep exchanging the elements while moving the markers in. And when the markers collide, we are done. Okay, so for 5, 2 and 1, exchange 5 and 1. You get 1, 2, 5. Now move the markers in. This will go here and this will go here. You see the markers have now collided. That means I'm done. So this was a quick example, but let's say I had a longer sequence, 7, 6, 5, 3, 1. So this has 5 elements. I start with 2 markers here and here and follow the same process. Replace, move in. 1, 7. 6, 5, 3 remains the same. The markers move in. Do the same thing. Replace 3 and the 6 and move the marker in. And moving the marker in collides it, and therefore this is done. And please remember, this is not a sorting algorithm. This is just an algorithm for reversing a sequence. But since the sequence that I'm looking for is guaranteed to be a descending sequence, just reversing is enough to sort it in ascending order. Alright, so rest should be quite easy. I have my position j over here, and until this everything is fixed. Now to the right of the j, I need to do this algorithm. So let me place my 2 markers. I'll place one here and one here. So let me call my markers r and s. I'll place my marker r, let's say here on the end. So r is equals to n. So this will represent this marker at the very end. And at the same time, I want to say another marker s should be at j plus 1. So this is my position j, and immediately to the next, I want to put my marker s. Now I have reduced to this problem. So what I do now, simply swap, move the markers in. And how many times do I do that? Until the markers collide. And by the way, remember in these both cases, I gave an odd number of elements. But it would not matter. Let's say I did not have the 5 over here. It would be exactly the same thing. 7, 6, 3, 1. Put the markers, move them in. You get 1, 6, 3, 7. You swap them. 1, 3, 6, 7. Move the marker in again. And now this time it collides on an empty space. So if the middle element is there, it will just remain there. It will not interfere with the process. And even if it doesn't exist, the algorithm applies exactly the same. So we want to do this process of swapping until some condition is met. So I want to say while, and it's quite simple. I'm going to say r is greater than s. You see, initially the right marker is on my r and the left marker is on my s. And I want to make sure that the right marker's position is greater than the left marker's position. And in this process of moving the markers in, eventually if this condition fails, either they will be equal or this marker will, overcome the other marker. That's when I need to stop. That is when the markers have collided. So while this is true, I simply want to swap. I want to interchange AR and AS. Okay, and that means we have already made the swap. All we need to do is to move the markers in. So for R, we'll decrease by 1. For S, we'll increase by 1. We'll say S is equals to S plus 1, and then R is equals to R minus 1. And this process will keep happening. The numbers will keep being interchanged until the markers collide. If eventually R becomes less than or equal to S, this while will no longer be true and will stop the interchanging process. We will be finished. And after following this entire procedure, A1 to AN is replaced by its next permutation. Alright, so this is the procedure. I hope it's clear. So the main steps are first this one, finding the first number that is not increasing when looking from the right. Once such number AJ has been fixed, out of the remaining numbers in the right, we want to find the number that is greater than AJ. Once that is found, we want to interchange, and after interchanging, the sequence will look descending, looking from left to right, or ascending, looking from right to left. But we need to reverse that, and we apply this reversal algorithm. In reversal algorithm, like we said, uses 2 pointers, swaps, and moves in. Alright, so we'll move into the next topic of the day, generating combinations. So here our goal is to be able to generate all different combinations from a set of n objects when r of them are taken at a time. Remember that in the previous algorithm we looked at the permutation of n things taken all at a time. But for combinations, see n comma n is a trivial problem. It is always equal to 1. Therefore we are more interested when a subset of n r objects are chosen at a time. Now I mentioned in the very first of the video that PNR is something that will not cover as part of the course, but I'll briefly mention this at the end of the video. So generating the items of P and R can be done by combining two algorithms. The algorithm for C n comma R that we're going to see shortly, and the previous algorithm for generating all combinations within those R objects. So we'll look into that in the end, but for now let's look into this specific problem where you need to generate all R combinations from a set of N objects. So our goal and approach will be pretty much similar to before. So let me quickly create the structure. I'm looking for an algorithm to generate the next combination, and I need to do that based on the current combination. And similar to before, let me show you an example first. Let's say I have this set containing 6 elements, the numbers from 1 to 6, and I want to generate 4 combinations. So combinations taken 4 at a time. And the idea of generating the combinations is still lexicographic order. In the problem for permutations, we considered all the permutations in lexicographic order. Here we're going to consider all the combinations. So that means as I'm generating, as I'm forming my dictionary, no two numbers will have exactly the same digits. That means all the digits must not be the same in any two numbers. So with that idea in mind, the smallest lexicographic ordering comes from 1, 2, 3, 4, given that I'm choosing 4 at a time. And the largest lexicographic ordering comes to 3, 4, 5, 6. This is going to be my last combination. For context, I'll also show you what we did previously. We had 3 numbers 1, 2, 3. We started with 1, 2, 3 and ended with 3, 2, 1. All of the numbers had exactly the digits 1, 2, 3. We are permuting between the digits, but we are doing so in a lexicographic order. Here we are taking combinations of 4 at a time, but we still want to be able to preserve the lexicographic ordering. And similar to the last problem, we'll define a next combination algorithm which will take any combination and give me what the next combination should be. And if I repeat that process, I can generate all the combinations until this last combination is reached. And needless to say, and I'm not mentioning it here, you must also understand the earlier correspondence between things and numbers. Earlier we argued that the permutations of n things taken all at a time is the same as the number of permutations of 1 to n, the numbers 1 to n. And similarly, any problem of combination or any problem of generating combination of a set of n objects and taking r at a time is equivalent to the problem of taking the set of n numbers 1 through n and finding all combinations of 4 numbers from that set. Okay, so with that context, we are ready to look at the process behind the next combination algorithm. We'll see first using an example again. So considering the same example, I have a set of 6 objects and I want to generate all the combinations choosing 4 at a time. And I know that I start with this one, 1, 2, 3, 4 and end with this one, 3, 4, 5, 6. Now let's assume that somewhere in my process, I reach this combination 1, 2, 5 and 6. And our question is, what should be the next combination after 1, 2, 5, 6? Let me remove this from here and I'll write it here. 3, 4, 5, 6 is going to be my last combination. Okay. Now in order to find this next combination, the first thing that I want to do is to compare 1, 2, 5, 6 with 3, 4, 5, 6 and find the last digit that is different. So what do I mean? So let me place 1, 2, 5, 6 right below 3, 4, 5, 6. I'll put 1, 2, 5 and 6 here. And if I compare these two numbers, the last digit that is different is in this position. And in my case, it would be the number 2. Because this 6 is the same as this 6, this 5 is the same as this 5. But this 2 differs. So I'm going to mark this 2. I'm going to put a marker over here. Now same as the previous algorithm, everything before this remains the same. So there's 1 on the left that will remain the same. Now whatever number was in the previous position will get increased by 1. So I have a 2 here. So I'll increase that by 1 in order to make it 3. Now I just want to consider the remaining positions. There are 2 remaining positions. I'm going to put the 2 remaining positions here. Now listen to this carefully. It doesn't matter here what numbers are remaining. I simply continue the pattern. I have a 3 here. I increment that by 1. I get a 4. Increment 4 by 1 again. I get a 5. So 1, 3, 4, 5 is going to be my next combination. So let's recall the steps again. So I have my current combination. And I should start with 1, 2, 3, 4. And for this example, we took 1, 2, 5, 6 as my current combination. So I want to compare that always against the last combination 3, 4, 5, 6. Or whatever the last combination should be in that example for that value of n and r. And I want to highlight the first digit that is different. And that would be when looking from the right. Now I'll leave everything to the left of it the same. So this one will be exactly the same as this one. And the highlighted position will be incremented. So the 2 becomes this 3 and every subsequent position is then incremented by 1. So after 3 comes 4 and then comes a 5. So let us see another example. We'll try to list all the combinations this time, but I'll reduce the set so that it's not too many combinations. So we'll consider 1, 2, 3 and 4. and we want to list all the possible combinations taking 2 at a time. So let me erase this and begin the process. I know that my first combination is going to include 1, 2, taking 2 at a time, and my very last combination is going to be 3, 4. And remember, there could be an overlap between these two combinations. For example, if I were taking 3 at a time, the first combination would be 1, 2, 3, and the last combination would be 2, 3, 4. So just be aware of this. But taking 2 at a time, this is my first and this is my last combination. Okay, so considering this is the first one, what will be the next one after this? So like before, we compare 1, 2 against 3, 4. 1, 2. So looking from the end, where is it different? See, it is different immediately over here. So leave everything to the left the same. So the 1 will remain. This 2 will be incremented. So 1, 3 will be the next combination. And now I hope you can see that 1, 3 will be compared against 3, 4. See, the comparison will always be against the last combination 3, 4. So now I'll be comparing 1 and 3, and still 4 and 3 are different. So this 3 will be incremented. That will give me a 1, 4. And finally what will happen? 3, 4, the last combination, will be compared against 1, 4. Now where is it different? It is not different here, but it is different over here. So this 1 will be incremented, and what will happen to this position? See, so the 1 will be incremented, I'll get a 2, and we know once it is incremented, the remaining positions will just be added by 1. So 2, 3, not 2, 4. So anytime we increment a position, every new position will just be obtained by adding a 1. And if we just follow this algorithm from 2, 3, comparing with 3, 4 again, we get 2, 4. Easy to see that. The next thing that we'll get is a 3, 4. So these will be the 6 different combinations that I need. So we'll do this algorithm next. I'll bring the previous example back. It's easier to see for the algorithm. We had 1, 2, 5 and 6, and the starting set had 1, 2, 3, 4, 5, 6. That would mean the ending permutation was 3, 4, 5, 6. So let us make some definitions. In this context, my value of n is equal to 6, all the numbers. My value of r is equal to 4. So the very first combination would be obtained by choosing the first r elements. So for the first 4 elements, the starting element was 1, 2, 3, 4. So in general, the starting combination will be A1, A2, all the way up to AR, taking the first R elements. So let me say this is the start. And what will the ending combination be? The ending combination will just take the last R elements. So in order to take R elements on the end, I must omit these elements. These will be n minus R elements. So where I need to start from will be n minus R plus 1, the next element after omitting the n minus R elements. And if I start from n minus R plus 1 and go all the way up to n, the last element, I will have chosen exactly R elements. So my end in this case, which is 3, 4, 5, 6, is represented by this sequence of a n minus R plus 1, and then the index of a increases again. It becomes n minus R plus 2, and it goes all the way up to the last element a n. And if we have any random combination like this 1, 2, 5, 6, we first compare it against the last combination, which is 3, 4, 5, 6. We find the last element that is different. This 4 will be compared against this 2 and found different. And this 2 will be incremented then to a 3, and every subsequent term will be incremented by 1. So 3 will give a 4 here and a 5 here. So let's replicate exactly the same process in an algorithm. So I'll say procedure, next R combination. I say next combination, but let's say next R combination, because we're choosing R things at a time from a set of n objects. And it will take any combination and generate the next one. So let's say the current combination is A1, A2, A3, all the way up to AR. So we are not saying you should always take the first R elements, but we are simply saying that any generated combination will have R total elements, and let this number represent that random combination. So given this is one of my combinations, what should the next combination be? And similarly as before, this should not be equal to the last combination. So we could say this is not equal to this value, but let's simply mention in terms of indices. We want to make sure that this sequence 1 to R is not equal to the indices of the last combination. And that is given by this set that it starts from this index n minus R plus 1, and then n minus R plus 2, all the way up to n. And what is the argument? This should not happen, because if this is the case, we have already reached the last combination. So just a trivial detail, but this is our main focus. We have this as our current combination and our goal is to generate the next. Alright, so let us recall our first goal in here. The first thing that we need to do is to figure out the end of the sequence. That will be the last combination. And we need to consider the last digit with the last digit of the current combination. And we need to keep doing that until we find that something is different. So comparing 3, 4, 5, 6 with 1, 2, 5, 6, we find that 6 and 5 match, but 4 and 2 do not match. We just saw it in the example. So in order to do that, I'll start by placing a marker at the last element in here, in the current combination. And I'll call this marker position I. So I'll initialize I is equals to R. Now let's see this carefully. Whenever I is equals to R, that means my marker is here in this 6. And this 6 should be compared with the last element in the set. And the last element I know will be in the nth position. So once we place the marker in the rth position, we'll write while AI is equals to n minus r plus I. And let's understand this. What does n minus r plus I mean? Or which position does it indicate? So we already know that n minus r is everything that was omitted. So when I was looking for the very last combination, 3, 4, 5, 6 in this case, the last combination also had to contain r elements. That means out of a total of n minus r elements would be left on the left. So if you look at the last combination, it really starts with n minus r plus 1. It goes n minus r plus 2. And you'd guess the next one would be n minus r plus 3. And therefore there is this increasing factor 1, 2, 3, etc. that we're trying to represent with this I. So when I is equal to 1, we'll be looking at a n minus r plus 1. And that would represent the first element of my last combination. But if you remember from earlier, we do not want to begin comparing with the first element. So it is not that we compare 3 with 1 first. We start comparing at the last element. And that is the reason I is initially set to r. You can see in this expression, if I plug I as r, minus r plus r will simply cancel. And I'll have n. And that is my last element. Okay, so if AI is indeed equal to n minus r plus I, that means this AI 6 is equal to n minus r plus I, which is also 6. We simply need to move the marker next because this time they were equal. We need to find something that is not equal. So let's move the marker left. We'll do I is equals to I minus 1. And whenever this loop terminates, because this is a process, this loop will keep going on until the numbers are matching. And as soon as they don't match, this while loop will break. And as soon as the while loop finishes executing, outside of the while loop, we have found the I that we're looking for. In this case, the I will be pointing at this 2. What we want to do now is to simply increment that by 1 and just keep adding 1 to find the next terms. So let us do that. We'll say AI is equals to AI plus 1. And please be careful, this is outside of the while loop. If you want, you can put a bracket here and here. But for writing only one line, the brackets are often omitted. Okay, and are we done? No, because we have simply changed this 2 into a 3. Now we need to also adjust the subsequent elements by increasing 3 to 4 and 4 to 5 until we account for all the remaining positions. So from the next one, from I plus 1 all the way up to the end, that is n. And let me use any variable. So I'll say for any variable, let's say j, and it starts from I plus 1 and goes all the way up to n. And for this loop, we'll simply assign aj. The value for that position in j should be modified. And we'll just say this is equal to ai plus j minus I. So doing it slightly differently. See here. So I have a 2 and I need to fill these 2 places. Now I know this is going to be a 3 and this is going to be a 4. All I want to do is to keep incrementing by 1 each time. But here, in order to tail a 4, I'm not taking a 3 and incrementing by 1, but I'm taking a 2 and incrementing by 2. Okay, that also works. So I'm not defining in terms of the previous element, but in terms of the very first element. So let's say this 2 is in my 1th position and I need this position, this one, which is my 3rd position. So I can simply take a difference of the positions, 3 minus 1, the difference is equal to 2, and I can add that. So hope that part is clear. So we are simply finding the difference between j minus I, which is the same as counting the number of steps we need to add, and we are adding it to the first element. And that will give any element in the jth position. But remember on the back of your head that all we are doing here is incrementing AI by 1 and finding the subsequent terms by just increasing the previous terms by 1. And yeah, this is the end. Once I do this, the original combination will be replaced. So I can simply say A1 to AR will be the new combination. So these are the 2 most important algorithms to look at. generating permutations of an object taken all at a time, and generating the next combination. And so before closing the video, we'll look at two little topics. One will look at generating all combinations. So this is also a very important concept, and we have already looked at this in the problem of counting subsets. So let's say I have three elements A, B, and C. So in the previous example, we looked at the algorithm of how to generate two combinations, for example. So we started with A, B, and we wanted to reach B, C at the end. Algorithm was pretty simple. We know B, C is the last one. So to find the next, we simply compare A, B with B, C. B and C is different. So highlight this position and increment by 1. So this will give me AC. And after AC, what do I get? So if I compare AC and BC, C and C are same. So increment A. So A incremented will give B and C will just be following B. So BC is indeed my last combination. So these three are the two combinations. But from this set of three, I could also generate one combination. So those will look like A, B, C. And I could also generate three combinations that would look like A, B, C. There also exists a concept of zero combination, and that will give an empty set or phi. Not choosing anything would result into an empty set. So if I want to generate all of these combinations, what algorithm can I use? And so for this one, the problem is the same as generating all subsets of a given set. So I have a set of elements A, B, and C, and I want to be able to list all of these 8 subsets. And one of the approaches to solve this problem, as we already know, is to implement binary counting. For 3 elements here, I'll just count in binary in 3 bits. So I'll start with 0, 0, 0, and I want to reach 1, 1, 1. So let me mention everything in here. And now I know that each of these numbers uniquely represents a subset. The first bit represents a A, the second bit represents a B, and the third bit represents a C. And if the bit is a 0, we should consider that the element is not included. And if the bit is a 1, we should consider that it is included. So which subset is this referring to? Do not include any of A, B, and C. That means I have phi here. If I have this is C. Include C, don't include anything else. Look at this. This is going to be B. This is going to be a subset containing B and C, but not A. This one is only going to contain A and nothing else. This is AC, AB, and ABC. So the task of generating all combinations from a set of AND objects is the same as the task of counting in binary in AND bits. And similar to the previous algorithms, we want an algorithm where we can plug in our current count and get what the next count should be. And if we are able to generate such an algorithm, we can start with the first combination represented by 0, 0, 0, and then keep generating each new combination until the last combination containing all ones is reached. So if you are ever asked in any question, devise an algorithm for generating all the possible combinations of all lengths from a set of n objects, you wanna begin with exactly the same argument like here. The problem of generating all combinations from a set of n objects is equivalent to counting in binary from 0 to 2 power n minus 1. That's going to be my last number, and the total count of subsets is going to be 2 power n. And we're going to do this in n bits. And you should perhaps write one more paragraph why this works, because the bits of each binary sequence can be used to decide whether or not to include a particular element into the combination. Okay, you should mention that, and therefore it should be sufficient if we provided a procedure to generate the next binary count in n bits. So we'll just mention that procedure here. We'll call this next bit string, and assuming we have n total bits, let's say my number is bn minus 1, bn minus 2, all the way up to b2, b1, and b0. So I'm starting with 0, ending with n minus 1. That is a total of n different bits. And if this is my current bit, what will the next bit be? And as per usual, we do not want this to be equal to 1, 1, 1 and all ones. Because if this is n ones, this is already the last bit string. Nothing follows this. Alright, so what is the main idea? What is the core idea? This algorithm is also pretty simple. We'll look from the right and find the first number that is not a 1. So if it is a 1, we just keep looking. If it is a 0, we stop. As soon as we find a 0, we replace that 0 to a 1, and everything to the right of it will be replaced by a 0. So let me show you, perhaps using this transition. So I have 1, 0, 1. So I keep looking from the right until I find a 0. So I found the 0 here. Everything before this will remain the same, okay? So the 1 will just be the same, and the 0 that I have found from the end will be replaced by a 1. And everything following this, no matter how many digits there are, will all be zeros. So 110 in my case is the next number. And let's look at one slightly bigger one just for the sake of contentment. So let's say I have this number 100111. So pretty simple. Look from the right, find the first 0. Here, copy everything to the left exactly the same. 10, change the 0 to a 1, 1, and everything to the right of it becomes a 0. So 3 zeros. So this is the algorithm that we want to implement here. So what do? So put the marker at the very end position. That's quite obvious. So I'll just start by mentioning that I should be equal to 0. Remember, the last or the least significant bit in this case is indicated by the 0th index. So I'm initializing I is equals to 0 in order to be able to point to B0 at the end. Now all I need to do is to check if it is a 0 or a 1. If it is a 0, I need to fix this number and numbers to the right. If it is a 1, I have not found a 0. I need to keep looking. So we'll just say while Bi is equals to 1, keep looking. While the value at my current marker is equal to 1, I'll need to keep looking to the left, trying to find a 0. But I know that once I find that 0, I'm going to eventually want to come back and replace that 1 with a 0, right? Because once I find my 0, I replace that 0 to a 1, and everything to the right of 1 will be equal to 0. So I can speed up my process, and when I'm looking from left to right, I can immediately convert these numbers into a 0 if I find a 1. So while Bi is equals to 1, I'll just say Bi is equals to 0. So reset that 1 into a 0 and move left. How do I move left? I move left by saying I is equals to I plus 1. I'm moving left, but in this case, this is 0, 1, 2. So in order to get to B1 from B0, I just increment by 1. So for every 1 that I find, I flip that 1 into a 0 and keep moving left. And that will give me these 3 bits. And eventually I'll reach this 0. Now this will not be equal to 1 and my loop will break. So when while breaks, the current Bi will be equal to 0, right? Because we have found a 0 that broke the loop. And everything to the right will also be equal to 0. So essentially, from this number 100111, we have reached here 100000. Flipped all of these ones and my marker is over here. So what do I want to do next? I need to change this 0 into a 1. So we are doing exactly the same thing, just in a slightly different order. So once this while breaks, I simply want to assign the value of Bi is equal to 1. So initially if it is a 1, keep flipping into a 0 and eventually you'll find a 0 and break. And when you break, flip that particular 0 into a 1. And this will give the next binary number. And remember, the bigger picture is to be able to see that this algorithm is equivalent to solving the problem of generating all combinations from a set of n objects. So same as before, we can say Bn-1, Bn-2, all the way up to B1, B0 is gonna be the next bit string. Alright, so this is all the formal section of the video. Before I close it, I'll get back to the promise that I made in the start, and that was about the permutation of n things taken r at a time. Although this is a very common algorithm and a formula, we never looked at this. And I mentioned that we'll not be looking into this in our course, but there is a reason to it. We have actually covered this indirectly. See, we have covered 2 problems already. We have covered the problem of the permutations of n things taken all at a time. And I'm talking in terms of generation, right? We are able to generate the permutations if we are given a set of n objects. So the first algorithm that we looked at today can do this. And then we looked into the second algorithm, which allowed us to generate the combinations of n things taken r at a time. And both of these, I'll repeat again, allow us to generate. So for an example, if I had a set like A, B, C, so this algorithm allows me to generate all permutations of 3. So that starts with A, B, C. And on the other hand, this algorithm of C and R required me to choose a certain R and then it would generate all the combinations. So if I selected 2, it would give me these 3 combinations, AB, BC, and CA. It would not give me AC because it is the same combination as CA. But I know that I am also able to generate P3, 2. The permutation of these 3 objects taken 2 at a time and not all 3 at a time. So if I do that, I get more permutations. I get BA, I get CB, and I get AC. So coming back to the question, why did we not study Pn, R? Or why is there no algorithm that we studied to generate this? The answer is we can combine these 2 algorithms in order to generate this. So in order to generate all the permutations Pn, R, you start by generating all the combinations Cn, R. Okay? So from A, B, C, if you want to generate permutations taken 2 at a time, first generate these combinations. And we already have an algorithm to do this. Now for the elements of each combination, we can generate all the different permutations that arise from that combination. And to do that, we can use the first algorithm, the algorithm of generating all the permutations of an object. So for a slightly bigger example, let's say I have A, B, C, D, and I want to generate all permutations taking 3 at a time. So I start by generating the combinations like I talked about. So it will be A, B, C, it will be A, B, D, I'll have A, C, D, and there'll be one more B, C, D. So these are all the 4 different combinations that are possible. I want to apply the first algorithm on each of these cases. So this will give 6 different permutations of A, B, C. I can generate 6 different permutations of these, taken all at a time, 6 over here and 6 over here. And by doing that, I will have successfully generated all the 24 permutations. So just remember that although we did not study P and R, it is a direct outcome of the 2 algorithms that we did. The combinations N, R and the permutations N, N. And the third algorithm of generating combinations of all lengths is also something that you might want to pay attention to. And with that said, we have completed this topic and the chapter. We'll start next video with a discussion of discrete probability. I apologize for the big gap in my publishing routine. I just had a few minor health concerns going on, but I believe I'm back on track and I'll be able to finish this course and upload more content. So thank you guys so much for watching. See you on the next one. Have a great day and bye.